Hey guys, this is Academic Chemistry, Chapter 5, Section 1, Models of the Atom. So in today's lesson, we're just going to introduce electrons' position in the atom, like within the electron cloud. Where we last left off, we just knew that electrons were surrounding the nucleus, so we're going to build that a bit more. So where we left off was the Rutherford model, and that was after he shot alpha particles at the gold foil. He had some of them come back, but most of them went straight through, so he knew that the atom was a nucleus with protons and neutrons in the center, and the electrons were circling around the nucleus, and he kind of thought of them like planets circling the sun. But the thing about that is it didn't explain chemical behavior. So in the model that Rutherford described, all electrons are circling at the exact same position almost with the same energies, and that's not true. Each electron is unique in its own address in the atom. So the Rutherford's model wasn't completely accurate. So it had to be further explained, and Bohr was the scientist to do that. So Niels Bohr, he described electrons in specific energy levels. So energy levels describe the maximum distance that an electron travels from the nucleus. So remember, this is this is the model. It's not just scale. This nucleus is super duper duper small. And then you have an energy level here. So you have a certain amount of energy to have an electron in the first energy level, the second energy level, etc. You can also call energy levels shells. So they literally kind of make shells and then a shell within that. Have you ever seen those Russian dolls where you have like they open up and there's a doll inside and a doll inside? So that's how I think of energy levels or shells of electrons, that they literally just encompass each other. So here we go. I can see, this is some great animations right here, but here is the idea of your atom and your electron kind of going around. Now keep in mind the atom is three-dimensional. So right now you're only seeing two-dimensional, right? Right and left, up and down, but the atom goes in and out of your screen as well. So the electrons don't just go in a circle. They kind of just go everywhere within the distance they're allowed. Each of these lines here represents an energy level. So that's the maximum distance an electron can travel away from the nucleus. So the first energy level is the closest to the nucleus. The second comes after that, third, fourth. It's going to go fifth, sixth, and seventh from there. So what I want to ask you is, why would being closer to the nucleus, so why is this a lower energy level? Why would this be an energy level of 1 versus this being 2, 3, 4, 5, 6, 7 would go out even further? And when you think about this, you have to think about what is an electron and what's hanging out in the center of the atom. So electrons that are hanging out here in the electron cloud, they are negative. So they want to be close to the protons hanging out here in the center of the nucleus because opposites attract. So all these electrons are wanting to be closer to the center. So it's going to take more energy to hang out outside. So it takes more energy to be further away from the nucleus. You can kind of think of it like, so when I was a kid, NSYNC was huge, right? And all my friends, they loved NSYNC. So if they were at the front row of a concert, that would be really great for them. But if NSYNC were these protons and my friends were out here, it would take a lot of energy to keep them out here because they would want to come closer to the center. So it takes, since they want to be around each other, since electrons are like, ooh, protons, you're super cool, then they're going to be comfortable closest to the protons, but it's going to take energy to pull them back or hold them further away from the protons because electrons want to be right next to the protons. So this is low energy and takes a lot of energy because these guys want to be all the way over here. So within this quantum mechanical model, it was updated by Schrodinger. And he said that within each of those energy levels, there are these things called orbitals. And orbitals are shapes or regions within each energy level where the electrons tend to travel based on how much energy they have. So first you had Bohr say, okay, it's just different levels. But then Schrodinger said, well, within those levels, you have different options as well. And these are those options. So these are the shapes in which an electron may travel. So here's the s orbital. P orbital kind of looks like two water droplets. Notice there's a node in the center, right? That's where the nucleus is. So the electron's not going to be there. D orbital has these 4 lobes. Some say it looks like a 4-leaf clover. Again, there's that node in the center where the nucleus is. And the F orbital looks like that. It's kind of a just big disaster. So you've got a sphere for the S, kind of like a dumbbell or a figure 8 for P, a clover, 4-leaf clover for D, and then F looks like a big old mess. So let's see how he came up with this. So if you tracked an electron, we have one specific electron, and this electron is in the s orbital. So if you continuously took picture of that electron, notice it's mostly in the center, but it also goes out here a bit. It wants to be closer to the center, because that's the nucleus. And this makes that spherical. You can clearly see that this looks like a spherical pattern. So this is one electron taking pictures over and over and over again. Remember, electrons are moving at the speed of light. They're going so fast. So this is just like a constant stream of pictures and then overlapping those pictures on top of each other. You can do that again for an electron in the p orbital, and you can clearly see those two lobes of electrons. Now, you can again see the electrons are more concentrated when they're in the center because they're closer to the nucleus, but once in a while they go out, but they don't ever go, notice they don't ever go up here or down here because the p orbital only has these two lobes. Here's our d orbital, and you can clearly see the 4 different lobes, again, most densely concentrated in the inside, but sometimes goes out here. And again, these are all tracking, each picture tracks one electron. So this dot here and that dot there, they're both the same electron, just traveled over time, and then all those images are superimposed. Here's the f orbital, and like I said, this one is just messy looking. It's just a big old mess. So the type of orbital, also called the cloud or subshell, each of these would be an orbital, an electron cloud or a subshell, depends on which energy or shell it's in. So remember, like I said, you have energy levels. Those are how far out from the nucleus, and within each of those energy levels, there's certain orbitals. So you can say within each shell, there's subshells. And each orbital can hold a maximum of 2 electrons. So in this s orbital, you can have 2 electrons. In this p, you can have 2. In this d orbital, you can have 2. And in this f orbital, you can have 2. All right, so if we look at this electron here, it is in the first energy level outside of the nucleus. So within the first energy level, we only have this s subshell. So it looks like a sphere. So that's the S. Make sure you draw the shape and label it so you get used to that. And since we only have one orbital, and each orbital can hold 2 electrons, the total number of electrons from this shape is 2, which totals 2 maximum electrons in the first energy level. That's all you got. The first energy level, 2, and then you move on. So if you have an atom with 1 or 2 electrons, it's going to be, those electrons are hanging out in the first energy level in an S shape. But if you have more than 2 electrons, you're going to fill this and then also move on to the second energy level. So once you have those 2 electrons in the first energy level, you have to move on to the second energy level. So let's see what things look like in the second energy level. You have one S shape, so one of these. There's also 3 different p orbitals. So these dumbbell shape, these are each a p orbital. So if you look at the total number, just the number of electrons from each shape, in S, you can have a maximum of 2. And that's always going to be the same. Whenever you have an S shape within an energy level, there's always going to be one orientation. So look, no matter how I turn that S, it's always going to look the same. It's a sphere, right? But this p orbital, like if you imagine my water bottle to be a p orbital, I could have a p shape this way, another one this way, and one going in and out, which is really awkward to hold, right? So there's 3 different orientations that you could have of the p subshell. So there are 3 options of 3 p's within your second energy level. So this can hold 2 electrons, this can hold 2 electrons, and this can hold 2 electrons. So from p, I can hold 6 electrons in my second energy level. So in the second energy level, within the p shape or p subshell, I can have 6 electrons. Totaling in my second energy level, I can only have 8 electrons, 2 in S, 6 in P. All right, once that's filled, so for your 2 electrons in the first energy level that we learned about the last slide, these 8, so after your first 10 electrons, you've filled up the first and second energy level, you have to move on to the third energy level. So that means not the first one after the nucleus, not the second one, but the third one out contains, if you're noticing a pattern, it does contain an S, It also has a P, a P, and a P. But now, additionally, you have a D shape. And there are 5 different D orbitals. All right, here they are. Now the fifth in the D shape kind of looks crazy. It looks like a donut with a dumbbell in between. It's just a little nutty. Remember, these are just what we observe in nature. It's not like some scientist was like, I want these to look this way. This is just how it works. So we're just writing these down. From S, you only have 1 orbital, and each orbital can have 2 electrons. So we'd have 2 in our S. So in 3S, there's 2. In energy level 3, in the P shape, there is 2, 4, 6 electrons. And energy level 3D, I've got 2, 4, 6, 8, 10. So if you total this up, the maximum electrons you can fit in the 3rd energy level is 18. You can also notice the pattern. The shape S has 1, and then P has 3, D has 5. It goes up by odds, like how many orbitals. And then if you double that, how many orbitals, that's how many electrons each. So now we're going to talk about the 4th energy level. So within the 4th energy level, you've guessed the pattern that there is an S shape. There are 3 different p orbitals, and there are also 5 different d orbitals. In addition to that, we also have F. Now you can probably guess how many F orbitals there are if you look at the 1, 3, 5, 7 pattern. Let's talk about the number of electrons from each orbital, or how many can fit total. There's only 1 orbital in S, so that's 2. There are 2, 4, 6 options in P, so I can put 2 electrons here, 2 here, 2 here. 2 electrons can go in each of these D shapes, so that's 10, and 2 for each of these F, so it's 2 times 7, which is 14. If you total up the total number of electrons that can fit in the 4th energy level, it would be 2 plus 6 plus 10 plus 14, so that gives you 32 electrons. Now we're going to figure out exactly what patterns these fill in, but right now you just need to know what shapes are in what energy level and how many electrons can fit. If you forget the order, it goes S, P, D, F. So S for 1st energy level, SP for 2nd energy level, SPD for 3rd energy level, SPDF for 4th. I think of the acronym Some People Dress Funny, so think of the order, right? SPDF, Some People Dress Funny. So 1st energy level is just S, 2nd SP, SPD, SPDF, okay? From there on, you would have the same SPDF options. Now we don't see necessarily these in naturally occurring atoms, but that's something that we might explore in the future. And these are the only shapes that we use for now in chemistry, but who knows what we will discover in the future. So best of luck learning electron configuration. This is this little intro, and we're going to get into a lot of specifics in the next few weeks. It should be a lot of fun. Okay, make sure you ask your teacher if you have any questions, and I'll see you in the next lesson.